Hello everyone, this is Mr. Lee. In this video, I'm going to go over distance and displacement. Alright, let's begin. So before we actually get into distance and displacement, we got to go over two definitions. The first one is called a scalar. Okay, and a scalar is a variable that it has only the magnitude. Okay, so a scalar is a variable that only has magnitude. Now, we have this new word here called magnitude. So let's define magnitude. Magnitude, it simply tells us how big / how small something is. And usually the magnitude is like a numerical value. Okay. Now, next we have this idea called a vector. Now, a vector is a lot like a scalar, except there's one big difference. A vector is a variable that has both, capitalizing that because it's important, the magnitude and the direction. Okay. All right. So we have our definitions here, and I just want to highlight a couple of things because this is what's going to be important for basically the rest of the course. Now, this word magnitude, it'll pop up everywhere. Whenever we solve a problem, if you see the word magnitude, you need to know what it is. Okay, and it's something, but it's just the numerical value of something. All right, now when we get into the more math-heavy stuff, the idea of a scalar and the idea of a vector will definitely come in handy. And knowing the difference between the two can really help out with your math. So let's do a couple of examples. The first one, let's say if we want to know what the temperature is, and I'm just going to use capital T as my variable for temperature. So this is my variable. All right, so if you look at the definition, we need a variable. So we got capital T. Let's say outside it's a nice spring 75 degrees Fahrenheit. Fahrenheit would be my units. Okay, and here, this is my magnitude. Now, before we continue, we need to make a very big, clear distinction. Okay, oftentimes when I ask for a variable, students give me the units and vice versa. A variable, and commit this to memory, a variable goes into equations. Okay, a variable goes into equations, and it is usually one letter. Okay, one letter. Now, units come after the magnitude. Right? And you can think of it as the descriptor. It's a descriptor of the magnitude. It tells us what the magnitude is. Like, for example, like the number 75, it could be a lot of different things. It could be like 75 apples, or 75 meters, 75 miles per hour. But the units help us define what that 75 is, and magnitude is just a number. Okay? All right. So this is a scalar. Now let's do a vector. So let's say I traveled, let's say we have a velocity, okay, of 5 meters per second, and let's say we are traveling north. Okay, so here v will be my velocity. Okay, v for my velocity, that's my variable. 5 is my magnitude. Meters per second, those are my units, and north is my direction. So if we take a look at the definition of a vector requires both magnitude and direction. All right. So velocity will be an example of a vector. Now let's compare that to something that is not a vector, but you can argue is very close to velocity, and that is speed. So s is the variable for speed, and we'll just use the same thing. We'll say 5 meters per second. So here, velocity is my vector, and speed is my scalar. Okay, and we know that this is my scalar because it has just magnitude. It doesn't have this direction. All right. So with that, that is one way of knowing if you have a vector or if you have a scalar. Now, the more and more as we get into the physics and you are exposed to vectors and scalars, a good method of knowing if it's a vector or if it's a scalar is by adding a direction to the vector. So for example, let's say, or to the scalar, excuse me. If we say we have a temperature of 75 degrees Fahrenheit, right? If we added a direction to it, such as left, that wouldn't make any sense, right? So this is a scalar, and by adding this direction left, we try to turn it into a vector, and that just doesn't work out, right? So this is a big fat no. All right, now whenever we go over new variables, I will always tell you if it's a vector or if it's a scalar, but another surefire way of knowing if it's a vector is the following notation. Vectors are written if you are given the variable. So let's use one that we just used, so we can say velocity. Okay, you will see this arrowhead on top of the variable. Okay, so this arrowhead tells us that it is a vector, and this is important because the arrowhead tells us the magnitude, and more importantly, the arrowhead shows us that there's a direction. Now, as we continue with the videos, you'll often see me write vectors like this. Okay, it's just, I don't know, my quick way of writing a vector. All right. Now, with vectors, we had this idea of a direction. So I want to go a little bit more into in depth with this idea of a direction. And when it comes to the different topics, I will also go over how the direction applies for that unit. Okay, so direction, we usually use a coordinate plane. And what a coordinate plane is the XY plane that we're all used to, right? So this is the Y direction, and this is the X direction. So we can say that anything going up, okay, will have a positive Y direction, and anything going down, we can say that there's a negative Y direction. Anything going to the right, we can say there's a positive X direction. Anything going to the left, we can say that there's a negative X direction. So let's use something that we are familiar with. So velocity, all right? So we can write velocity as 5 meters per second. Okay, now this right there tells us that this velocity has a positive direction, because there's a positive symbol in front of the 5. Now we don't write it because it's like known that there's a positive symbol there, but I'm just putting it out there. If you don't see it, it's usually a positive direction. We can also say that it's 5 meters per second north or up. Okay. We can also say 5 meters per second right. So these are all examples of vectors. Now on the flip side, we could also write it like this: negative 5 meters per second. And this negative will be the direction. Now this can be the same as, let's see, 5 meters per second left, okay, or down is all the same. Now you could also write it like this: negative 5 meters per second left / down. Now this is just really covering your bases so that the audience knows that we are talking about the negative coordinate. Okay, all right, so that's direction. Now with vectors and scalars out of the way, let's go over distance and displacement. So with distance, or let's do position first. Position. All right. Now it's important to know that when you are given a new terminology, you know the variable that is associated with it. So for position, we say that position is represented by the letter x. X is the variable for position, and the units will be in meters. So meters. Okay, I'll put that into the definition. All right. So position is a lot like X marks the spot. It tells you where you are located relative to a fixed point, often called 0 meters. All right. So position is X, and we can say that the units are m for meters. Okay. So this is position. When it tells you that it is a relative location from a fixed point, often called 0 meters. So if we were to give you a coordinate plane, oh boy, that's not a straight line. All right, a coordinate plane like so. okay, where this is the y and the x. If you are located here, we can say that your position is, I don't know, let's say this is coordinate 5, 0. Okay, so if I were to ask you where you're located, you can say I am 5 meters away from the origin, and the origin, of course, being right here in the middle. Now, we can also put you somewhere else along the coordinate axis. We can say you're right there. And if I were to ask you, where is your position? You can say, well, I am located at coordinates 4, 7. Okay, and so I will know exactly where your position is. All right, you are 4 meters north and 7 meters to the east of what we're calling the origin. All right, now what about distance? So distance, there's not a fancy physics definition for distance. It's what we know and how we use distance in our everyday language. So let's come up with a everyday kind of definition for distance. All right, so distance is the magnitude of the displacement traveled between two positions. Okay, so here we have a new word, displacement, and I want to define both distance and displacement at the same time so that you can get a real good sense of it. But before we do that, before we get to displacement, let's do a quick little idea of what distance really tells us. Okay. By the way, the unit for distance is units are meters, for meters, and variable is lowercase d. Okay. Now, oftentimes you won't use distance; you'll use displacement, but just in case, this is how we can solve for a distance problem. All right. So let's say we have a axis, and let's say this is our 0 meter mark, and let's say that Mr. Lee is located at position x is equal to -5 meters away. Hello, that's me. Hi. Okay. So I'm right there at -5, and I travel to, let's see, on my travels, I'm going to use red here. I go up, 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 up. I travel to the 0 meters. Who knows why? I'm picking up a pencil, and then I go back to my original starting. Okay, my starting position at -5. So if I were to ask you, what is my total distance? You can say, well, Mr. Lee traveled 5 meters to the right, and then he traveled 5 meters back to his starting position. So his total distance is 10 meters. Okay, now notice here, there's no direction, so we can say that distance is a scalar. All right, so that's distance, right? It doesn't care about any kind of direction. It's just the total amount that you traveled. All right, now what about displacement? So here we have a brand new terminology, displacement. So displacement is going to be represented as, I'm going to write this one in. So displacement is, how we can define displacement is the change in position of an object. Okay, and the units for displacement is also m for meters. All right, so I'm going to write in the variable here for displacement. Now, within the definitions of physics stuff, we can often find the equation. So we have change in position. So change is represented by this triangle. This is a Greek letter called delta. Okay, and delta means change. Delta is change. And whenever you see delta, there's a very specific formula that comes with it. Delta means final, whatever variable, minus initial, whatever variable. Okay, and so for here, we can write displacement as delta x, because it's the change in position. Okay, and so what this means for us, if we were to write this out in a formula, delta x, it's final variable, so final position minus initial position, and these are little subscripts. They're the tiny letters that go below the variable. It will always be within this format, final minus initial. Okay, so this is the change in position of a object. So if we take a look at the original scenario above, where I traveled 5 meters to the right, okay, and I go back to my original position. So if I were to use my equation, all right, for my above scenario here, we can say my final position was -5. Oh, by the way, this is a vector. Okay, -5 minus my initial position, which was -5. Now, if we were to do this mathematically, we will get -5 minus -5, and that just turns into positive, so we can get -5 plus 5, which gives me 0 meters. So what this tells us is that I had no change in position. It's as if I didn't move at all. Okay. Oftentimes is also described as the shortest distance between your start and your end. So let's do another example. Let's say we have a coordinate plane this time. Let's say we start off at 0, 0. Okay. And I'm going to take us for a wild ride. Right. We're going to go all over the place. Right. This is our path. Okay, so what we're doing is we're chasing a cat around, right? We're chasing the cat around. Oh, hello, right? We almost got there. Why are we chasing this cat? No one knows. But what we do know is that we end up right here. Boom. Okay, and what is that spot? So this spot right there, we can say that our final position is xf is equal to, let's make it simple, 2-0. Okay, and so our final position, or excuse me, our displacement, our final position was 2, okay, minus our initial position, which was 0. So our displacement is 2 meters. Now this is important here. I'm going to use a different color. Let's use green. So this entire journey, right, of us chasing the cat, displacement doesn't care about that. Displacement only cares about your starting and your ending position. So what that means is if we were to ignore everything that happened in between, it's as if we just walked like this. Boop, and we ended up there. Everything else in between, that doesn't matter. Where that matters is the distance. Okay, so our distance, so even though our displacement is 2 meters, I don't know, our distance, we could have traveled 275 meters while trying to chase this cat. Okay, but the only thing for displacement that matters is your final and your initial position, but distance cares about the entire journey. Let's put that down. This is a entire journey. Okay, and this tells us the shortest path. Okay, so it's almost like, you know, if you wanted to take the scenic route versus the direct route. Always take the direct route will be displacement, scenic route will be the distance. Okay. All right, so I mentioned this coordinate plane here. We can also use the coordinate plane to find the distance and displacement. So let's try that. If I have a coordinate plane, okay, and let's say we start off here at 0, 0. All right, I'm going to use my different colors, and we travel to the right, okay, and we end up, let's say this is 3, 0, and then we travel up. Let's do red. Okay, we travel up. Okay, let's say we travel 4 meters up, so this will be 3, 4, right? And I were to ask you, okay, what is my total distance? All right, so my total distance, remember distance only cares about the total traveled, okay, doesn't care about any direction. We can say we traveled 3 meters initially, right, 3 meters, and then from there we traveled upwards of 4 meters. So for my total distance, I can say we traveled a total of 7 meters. Now what about displacement? What about displacement? Well, remember, displacement cares only about the final location and your starting location. So it's as if we took this diagonal path instead of going right and up. Now, in order to solve for this, okay, there's 2 ways of going about it. We can find our displacement for the x-coordinate and the y-coordinate, and then use that to find the Pythagorean theorem. So let's try that. So our displacement in our x-coordinate, right? Our final x coordinate is 3. You know what? I'll do this correctly. So xf minus xo. I always like to write out the equation without any of the numbers first. Okay, our final x-coordinate is 3 and our initial x-coordinate is 0. So our displacement along the x-axis is 3 meters. Now see what I do here? Instead of writing delta x, I'm going to write delta y to show us that we're doing a change in y position. So our final y coordinate was 4 meters. No, excuse me, let me do this correctly. So we get y final minus y initial. Our final y coordinate is 4. Our initial y coordinate is 0. Therefore, our displacement in our y-axis will be 4 meters. All right. Now we have both the x and the y. In order to find the actual displacement, we're going to use some trigonometry magic, and this is something that we'll be using all the time. So right there, this is a right triangle. And oftentimes when we're dealing with x and y coordinates, we can come up with right triangles. And the method of solving it, after you have the right triangle, we have to use the equation made famous by a very famous Greek guy, Pythagoras. And his equation states that c squared is equal to a squared plus b squared, where c is the hypotenuse. Okay, and let's just make a the x-axis or the x variable, and b can be the y-axis, okay, or the y variable and the x variable. So if we were to apply this formula, we can say that the total displacement, okay, c squared, is equal to a squared, which is my x, so 3 squared, plus b squared, which is my y, 4 squared. So 3 squared gives us 9, 4 squared gives us 16, for a total of 25. Okay, but we want to know the actual displacement, so take the square root of that, and we get 5. Okay, so our total displacement was 5 meters, but our total distance was 7 meters. So you can see how the displacement here is not the same as the distance. All right, that's that for distance and displacement. This is going to be the start of our journey into the kinematics unit. I'll see you next time. Bye-bye.